In this video, we are going to talk about chapter 5, which is internal memory. In this chapter, there are many two operations which can be done to the memory cell, which is the write and the read operation. In the next slide, we will see about the different types of semiconductor memory types, which consists of RAM, read-only memory, programmable read-only memory, erasable PROM, electrically erasable programmable read-only memory, and flash memory. These are the categories of which each type of category they belongs to. For example, read-write memory, read-only memory, and read mostly memory. And behind are their characteristics about which depends they are whether erasable or how they are write into how the data is write into the memory, and whether they are volatile or not. And we will discuss further about that. In the next slide, we will discuss about the dynamic the dynamic random access memory, which will be simplified as DRAM. Random access memory technology is divided into two technologies, which is dynamic and static. The dynamic random access memory, which is DRAM, is made with cells that stores data as charge on capacitors. The DRAM is required periodic charge refreshing to maintain data storage through transistor, and the term dynamic refers to the tendency of a stored charge to leak away even if the power continues applied. This is the cell diagram of the dynamic RAM structures, and next we will talk about the static RAM, which is SRAM. It's a digital device that uses the same logic element used in the processor, and their binary values are stored using traditional flip-flop logic gate configurations, and will hold the characteristic of SRAM is that will hold its data as long as the power is supplied to it. Now, this is the structure of the static random access memory. And next we'll see about the difference between SRAM and DRAM. For SRAM and DRAM, they are both volatile, which means that power must be continuously supplied to the memory to preserve the bit values. Well, for the dynamic, which is a DRAM, it's simpler to build and smaller. It's more dense, which means a more cell unit per area, and is less expensive, and it requires a supporting refresh circuitry, and it tends to be favored for large memory requirement and normally is used for the main memory, while for the static RAM, which is a SRAM, is faster and normally is used for cache memory and both on and off chip. In the next class, we'll talk about the read-only memory ROM. It contains a permanent pattern of data that cannot be charged or added to, so there is no power source is required to maintain the bit value in the memory. The data of program is permanently in the main memory and never needed to be loaded from a secondary storage device. The data inside ROM is actually wired into a chip as part of the fabrication process. However, there's a disadvantage of using the ROM, which is there's no room for error. If one bit is wrong for the whole batch of ROMs, and then the whole ROMs will be thrown out and it's wasted. And the data insertion steps includes a relatively large fixed cost, which is very expensive to maintain a ROM. Next, I will talk about a programmable ROM. It's a less expensive alternative compared to the ROM. It's non-volatile and may be written into only once. The writing process is performed electrically and may be performed by suppliers or customers at a time later than the original chip fabrication. However, writing into the programmable ROM is required special equipment, and programmable ROM provides us a flexibility and convenience and is attractive for its high volume production runs. Next, we'll talk about read-mostly memory. Read-mostly memory is containing the erasable programmable read-only memory, electrically erasable programmable read-only memory, and flash memories. For the EPROM, the erasing process can be performed repeatedly, which means we can keep on updating our data. It's more expensive than the PROM, but it has the advantage of multiple update capability. For the EEPROM, which is an electrical erasable programmable read-only memory, it can be written into any time without erasing the important contents. It's a combine the advantage of non-volatile with the flexibility of being updatable in place, which contains the advantage of the EPROM, but it's an upgrade version. However, it's more expensive than the EPROM. About flash memory is in the middle between the EPROM and EEPROM in both cost and functionality. It uses an electrical erasing technology and does not provide byte level erasure. Next, we'll talk about the interleaved memory. It is composed of a collection of the DRAM chips and is grouped together to form a memory bank, which is here. They form a memory bank here, and each bank is independently able to service a memory read or write request. And if the consecutive words of memory are stored in different banks, the transfer of a block of memory is speeded up. The next slide we'll talk about error correction. For error correction on hard failure, which always occurs in a hard way, it will be the permanent physical defects, and memory cells or cells affected cannot reliably store data but become stuck at 0 or 1 or switch erratically between 0 and 1. This error can be caused by the harsh environmental abuse, manufacturing defections, and the wear of the machines. But sometimes the error consists of soft error, which occurs in the application. This is due to the random and non-destructive event that alters the content of one or more memory cells. This error would cause no permanent damage to the memory, and it can be caused by the power supply problems or alpha particles. The Hamming error correction code, which is the most normal way that how we use to check the error correction. I will explain how to do the Hamming error correcting code in the end of the video. So we'll just move on. This is one of the example of the Hamming code check bit calculation. First of all, we are given a data word, which is 00101101010111, and we are also given a retrieve check bit, which is 00101. So first of all, we fill in the bit position, which will be like this, and position number, data position. I'm sorry for misinformation earlier. This is an example of our Hamming code calculations, check bit calculations. So this is the data word they're given to us, and this is the result we will get after we finish the calculation. First of all, we will find a check bit using the formula. First of all, we will construct a table following the bit position, position number, data position, check position, original word, original check bit, retrieve word, and retrieve check bit. And then we will fill it one by one. First of all, we will find a check bit size, which is using the formula 2k minus 1 and larger or not equal than m plus k. So from the formula, we know that there are 17 bits, and then we'll fill in all the position number into the bits, and also the data position of them, and also the check bit position. Thus, after that, then we can begin our calculation for the check bit. So for the check one, we're using all the dy out, all the we're using all the data position which have a similar bit check bit with the check position, which is d1 and d2, d4, d5, d7, d9, d11, and d12. After we fill in, and then we fill in the bit, and using the sign magnitude, and then we can find the check bit. Then we using the same method for the other 4 check bit, which is filling the position regarding their fill the data position regarding their check position. Then we can get the final final check bit for the calculation. And then we'll find a syndrome word, which is we'll use the result we get from A, and then we plus our retrieve check bit, check bit, and then we will get this is our syndrome word. Then our retrieve word, and then we will make the change in our table on the syndrome word, which is 00101 in the bit position 5. Therefore, we will change the bit into 0, and therefore this is our retrieve word, and the Hamming code calculation is complete.